Hey everybody, limits differential calculus, day number 8. Topic for today is related rates. We're going to use our skills in implicit differentiation and some problem solving to get it going today. All right, let's get started. All right, in these problems, what I'd like to do is highlight what I'm trying to find, what I'm given, and when it is that I'm trying to find said thing. So problem number 1. A 25-meter long industrial ladder is leaning against a wall on the side of a building. Let's make a quick sketch. Here's the building. Here's the ground. Here's the ladder. 25 meters. Okay, now the bottom of the ladder starts to slip along the floor at a rate of 0.2 meters per second. I'm going to call the bottom of the ladder X, and I'm going to call the vertical portion of the ladder Y. Okay, now, before I get started with anything here, what I do want to realize is that I'm going to use the figure given in order to relate the variables. So I would say that x squared plus y squared is equal to 625 using the Pythagorean theorem. Okay, let's continue reading. So the bottom of the ladder starts to slip along the floor at a rate of 0.2 meters per second. So that's what's given. So that's dx dt is 0.2 meters per second. Determine how fast the top of the ladder is moving down the wall at the moment when it is 20 meters above the floor. So when y equals 20 meters, we want to know what dy dt is. Okay, now a couple of things. If you know your Pythagorean triples, you know that if y is 20, then that means that x must be 15. Okay, that's a 3, 4, 5 triangle just scaled by a factor of 5. Okay, now I believe I'm ready to work. So I'm going to take the derivative of this expression here, this implicit relation, and write it out. So 2x times dx dt plus 2y times dy dt is equal to the derivative of 625, which is 0. My goal here, you guys, is to find dy dt. So I'm going to plug everything that I know in for x, dx dt, and y. So x is 15, dx dt is 0.2, y is 20, and I'm trying to find dy dt. Okay, since y is headed, the top of the ladder is coming to the ground, I know dy dt should be negative. So I'm going to get 30 times 0.2, which is 6. Yeah, I believe that's right. Yep, 6 plus 40 dy dt equal to 0. I'm going to subtract and divide. So dy dt is equal to negative 6 over 40, which reduces to negative 0.15 meters per second. Okay, so the top of the ladder is moving downward at 0.15 meters per second when the top of the ladder is 20 meters above the floor. That's your interpretation right there. Okay, let's move on to another example. Okay, it looks like we've got a 3-pronged problem here working with a rectangle. Okay, so let's draw our rectangle with a length and a width. Okay, let's call this W, let's call this L. Okay, so the length of a rectangle is increasing at a rate of 3 centimeters per second, and its width is decreasing at the same rate. So given dl dt is equal to 3, and dw dt is equal to negative 3, If the length and width of the rectangle are 24 and 7, so the length is 24, the width is 7, find the initial rate of the following. So the area, we're trying to find dA dt. Okay, so let's look at the area equation. So the area will be length times width. Therefore, dA dt will be dL dt times W using the product rule plus L times dW dt. Okay, I'm going to plug the appropriate values in. So dA dt will equal dL dt times W plus L times dW dt. Okay, so looks like as the length increases by 3 meters per second, centimeters per second, and the width decreases by -3 centimeters per second, okay, what we're going to get for the area, it will be changing. Okay, so I'm going to add these together. That's 21 plus -72, which is a -51 centimeters squared per second. So the length was already longer and now it's getting bigger. The width was smaller and getting smaller. So it would make sense that the area overall would be decreasing, right? So we're squashing, and of course my drawing isn't to scale, but we would be squashing the rectangle. Okay, now for perimeter, we're going to find dP dt. We're going to have all of the same parameters, no rates change. It looks like the lengths and the widths will stay the same as well. So let's talk perimeter. Perimeter would be 2L plus 2W. So dP dt would be 2 dL dt plus 2 dW dt. So if we think about perimeter, if both the length and the width are changing at the same rate except in different directions, it would make sense then that the perimeter would not be changing. Okay, so the perimeter is not changing if the length and the width are changing at the same rate in opposite directions. Okay, let's equate now this to the diagonal length. Okay, so the diagonal length will have a specific relationship. I'm going to call the diagonal capital D. Of course, nothing is changing with our givens and our whens. So the diagonal squared is equal to the length squared plus the width squared using the Pythagorean theorem. So I'm going to take and derive this implicitly. So that'd be 2 times D times dd dt, 2 times L times dL dt, plus 2 times W, oops, let me regroup that, 2 times W times dW dt. Okay, let's plug in values that we know. If the length is 24 and the width is 7, another Pythagorean theorem or Pythagorean triple would tell me that the diagonal is 25. Okay, so I know then that I would have 2 times 25, which is 50, times dd dt would be 2 times the length, which would be 48, times dL dt, which is 3, plus 2 times the width, which would be 2 times 7, which is 14, times dW dt. Okay, so I would get 50 dd dt is equal to 102. That tells me that dd dt would be 102 over 50, which is 2.04 centimeters per second. So the diagonal length is increasing at 2.04 centimeters per second. Awesome. Okay, let's look at another example. Okay, the volume of a cube is increasing at a rate of 1.5 cubic meters per second. So dV dt is given 1.5, ooh, that was a weird 5, let's try it again, 5 meters cubed per second. Either notation is fine with regards to meters cubed per second. Determine the rate at which the surface area of the cube is changing. So dSA dt, when the volume is 27 meters cubed. Okay, now if the volume of a cube, which is side cubed, right, if I draw myself a above average cube, side times side gives me the volume. So if the volume is 27, then the side length must be 3. Okay, so I'm going to use that to give me some information. Okay, now volume again, let's work with that. dV dt is equal to 3s squared times ds dt. Now you might think, why would you need that? And the reason why is because it's coming up with regards to the surface area. So dV dt is 1.5. S we said was 3. I'm going to need ds dt, and just through experience, you'll kind of see what's going on here. But I'm going to take and divide by 27. That'll be ds dt. So that'll be meters per second. Now, why would I need that? Because the surface area of a cube is 6s squareds, right? Each face is a cube, or is a square. S squared would give me the area of the face, and there's 6 of those. So the derivative of the surface area with respect to time would be 12 times s times ds dt. And you can see that I would need ds dt. So the change in the surface area with respect to time would be 12 times s, which is 3, times ds dt, which is 1.5 over 27. Now if we reduce this is actually quite awesome. This actually comes out to be exactly 2 meters squared per second. Absolutely sweet. Okay, let's move to the next problem. All right, air is being pumped into a spherical balloon at a rate of 7 centimeters cubed per second. 7 centimeters cubed per second is our given. Find the rate of change of the balloon's radius. That's dr dt. When the volume of the balloon is 36 pi. Kind of sketchy there with the pi spelled out, but whatever. Okay, so you'll be given formulas. Of course, you'll have your formula sheet for exams. But when it comes to volume and all that stuff, you'll have what you need. So the volume of a sphere is 4/3 pi r cubed. Okay, so if our volume is 36 pi, then 3/4 of 36 is 27. I'm going to drop the pi's, and it looks like our radius is 3 centimeters. Okay, so let's look at the volume. That should be dV dt. Okay, thanks for labeling that. Nice work. Pi r cubed, let's find dV dt in terms of r and dr dt. So the 3 will come down, reduce with the 1/3. So that'll be 4 pi r squared times dr dt. dv dt is 7. R we know is 3. dr dt is what we are seeking. So it looks like, 3 squared, sorry. So it looks like I will get 7 over 36 pi, yep, is equal to dr dt. All right, that's not necessarily a pleasant answer, but dr dt, of course, will be centimeters per second. I would leave it just like that unless told to do otherwise. Okay, so let's take a look at number 5. A beacon on a lighthouse 100 meters from a straight shoreline rotates 6 times per minute. Okay, so let's give a little sketch here. Here's a beacon on a shoreline 100 meters from another shoreline, and let's say the spot perpendicular to the beacon's light on the other shoreline, let's call it point A. Okay, it says that it rotates 6 times per minute. Okay, so d theta dt is 6 revolutions per minute. All right, anytime you're working with d theta dt, in order to get the correct units for, in this case, what will be dx dt, and I'll show you what that's going to look like in a second, you have to put d theta dt into the correct units with regards to your unit of time, which we're going to use seconds here in a minute, as well as we want to convert revolutions to radians. So I'm first going to convert d theta dt into revolutions per second. So d theta dt, if I divided by 60, I would get 0.1 revolutions per second. And then if I multiply by 2 pi, since a revolution is 2 pi units, or 2 pi radians, d theta dt, 2 pi times 0.1 is 0.2 pi radians per second. So that's key, you guys, key to get into radians. Okay, so it's asking in this question, at least in part A, how fast is the beam of light moving along the shoreline at the moment when the beam and the shore are perpendicular? So we want to know, let's sketch this out. We got a nice right triangle. Here's theta, and here is x. So we want to know what the speed of the beam of light is when it is at point A. Okay, so when it's at point A, what is the value of x? Well, x will equal 0. Okay, so let's do a little bit of work here. Notice that I've got a nice right triangle, so I can write a trigonometric equation using the right triangle, which will be tangent theta is equal to x over 100. And now I can differentiate. And when I differentiate with respect to t, the derivative of tangent theta is secant squared theta times d theta dt. The right side of the equation will be 1 over 100 times dx dt. Now, I know that I'm going to be seeking dx dt. It is the rate of change of the beacon of light as it passes through point A. Okay, so a little bit of work we got to do here. If x equals 0, then theta equals 0, which is helpful. So I'm going to plug a 0 in for theta, so that'll be secant squared of 0 times d theta dt. D theta dt we determined was 0.2 pi. I've got 1 over 100 times dx dt. So if you're asked to leave this in exact form, dx dt would equal, oops, this should have been a 0 here, would equal 100 times secant squared of 0 times 0.2 pi. Okay, so secant squared of 0. Well, secant of 0 is 1, so secant squared of 0 is 1. So dx dt would be 20 pi. And since we're in radians, we can be very confident that we would get the measurement of meters per second. Okay, now if that was out to 3 sig figs, that would be 62.8 meters per second. Okay, outstanding. Okay, so just to kind of go back on what I was saying, make sure you're in radians. Make sure your change in your angle with respect to time is in radians. Okay, let's look at part B. It says find how fast the beam is moving along the shore when the beam hits the shoreline 50 meters from the point on the shore closest to the lighthouse. So now the only change here is that x is going to be 50. Okay, I'm not going to re-sketch everything. I'm going to use the exact same setup. Tangent of theta equals x over 100. That means secant squared theta times d theta dt, which hasn't changed, should equal 1 over 100 times dx dt. So what has changed if x is equal to 50? Okay, so let me change this to a 50. Okay, if that's a 50, then using Pythagorean theorem, I'm not going to show the math here, but the hypotenuse would be the square root of 12,500. Okay, so if that's true, then I can find the secant of theta. Well, the secant of theta is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so the secant would be hypotenuse over adjacent. Now if I square that, secant squared theta comes out to be 12,500 over 10,000, which comes out to be 1.25. Okay, now we got a little bit of work we can do here. If secant squared theta is equal to 1.25, and d theta dt hasn't changed, it's still 0.2 pi, and nothing has changed on the right side, then dx dt should be 1.25 times larger than dx dt in part A. So we should get 25 pi meters per second. Out to 3 sig figs, that would be 78.5 meters per second. Okay, let's look at part C. Interesting question here. What is happening to the velocity of the light beam when the ray is parallel to the shoreline? Okay, so let's first of all think about, here is the beacon. Here was what we called point A. Okay, so let's think about this logically. What are they asking? They're asking, well, what would the speed of the light beam be as it's shining here? Well, how would it get there? Well, it would have to go along the shoreline across from it. So first it would have to be at x1, then at x2, then at x3, etc., until it gets out to some point here, and it's eventually going to head to where theta is approaching pi over 2. Okay, so let's look at this setup. Let's first of all look at dx dt. Dx dt ended up being secant squared theta times d theta dt, which hasn't changed, times we ended up multiplying by 100. Okay, so let's look at how this changes, or what the limit is as theta goes to pi over 2. Okay, so we're looking at the limit as theta approaches pi over 2 of dx dt. And that should be able to answer for us this question. So the limit as theta approaches pi over 2 of the expression, let's combine some items here. That would be 20 pi times secant squared theta. Okay, so what is secant doing as theta approaches pi over 2? Well, let's look at cosine in order to figure that out. Here's pi over 2, and here's pi. So what does cosine do? It goes from 1 to 0 to negative 1. Not my best sketch. However, how is secant related to cosine? Well, at pi over 2, secant has a vertical asymptote. So secant squared would also go to an uncountable value. Therefore, the limit as theta approaches pi over 2 of dx dt does not exist. Okay, so since that's true, we can say that dx dt is inconclusive. I'm going to shorten that. Inconclusive as theta approaches pi over 2. What that really means is that we can't determine how fast that light ray is moving as the beacon shines parallel to the shoreline. Okay, we got one more example here, and then that'll be it for this lesson. All right, very interesting example here. It says an isosceles triangle with sides 6 centimeters, 5 centimeters, and 5 centimeters is going through a transformation in which the longest side is decreasing at a rate of 0.1 centimeters per second. So it says find the rate of change of the angle, and I'm actually going to call that angle C. So I want to find dc dt. Okay, that's angle C. I'm given, and I'm going to call my given, this rate, d lowercase c dt, negative 0.1 centimeters per second. So capital C is the angle, lowercase c is the side. I want to know the rate of change of the angle opposite the changing side at the start. So that's when lowercase c equals 6 centimeters. I'm going to call the other two sides B and A. Those are both 5 centimeters. Okay, so how can I relate an angle to a side when I'm given 3 sides? Well, if you don't recall, you can use the law of cosines. And the law of cosines in a situation like this. I'm going to call this side C, which is equal to 6, side A, which is equal to 5, side B, which is equal to 5. I'm going to call this angle C. So C squared is equal to A squared plus B squared minus 2AB cosine of angle C. Okay, now let's think about what is constant and what is changing. Our two variables are the two C values, right? Side C is changing, and so is angle C at the same time. A and B are constants. So I'm going to differentiate with respect to time both sides of this equation. That'll give me 2 times C times dc dt. The A squared and the B squared will drop off. Okay, so those will be gone. Those will go to 0. However, A and B will stay on the third term due to the fact that it's a coefficient of cosine. So the derivative of cosine is negative sine. So that'll make this a positive 2AB sine of angle C times dc dt. Okay, and that's what I'm looking for, dc dt. So I've got a couple of things I've got to do. Okay, the first thing is the following. I got to find out what angle C is when side C is 6. So I'm going to do that over here. This angle is the angle C over 2. because I've got side c over 2 is 3, and a is equal to 5. So c over 2 is equal to the inverse sine of 3/5. I don't know what that is, and actually I really don't care. Angle C is then equal to 2 inverse sine of 3/5. Make sure your calculator is in radian mode, please. Okay, now let's do some subbing. So C is equal to 6, A and B are equal to 5. That would make this equal to 12 dc dt, which we know as negative 0.1. 2AB is 2 times 5 times 5, which is 50. Ooh, I almost put 25. 50 sine of 2 inverse sine of 3/5 times dc dt. Okay, so I've got a little bit of math to do here. I'm going to divide, and I'll put that formally in this form. dc dt, negative 0.1 times 12 is negative 1.2 over this whole expression, 50 sine 2 inverse sine of 3/5. That'll be dc dt. Now, of course, you need a calculator here, and your answer here will be in radians per second. With my calculator, that comes out to be negative 0.025. Okay, let's look at part B and see how this is slightly different. Part B states for us that the rate of change of the angle opposite the changing side, so same scenario, except when the triangle is equilateral. So I'm still looking for dc dt of the angle when dc dt for the side is negative 0.1 per second. And I put, nope, yeah, we're good. Okay, when the triangle is equilateral, just meaning that A is equal to B is equal to C is equal to 5. Okay, so I'm going to skip right to it. I'm not going to write out the law of cosines. I'm just going to write out 2c dc dt. Again, A and B are constant, so those are going to drop off. So I'll get 2ab sine of angle C times dc dt. Okay, so if all three of those are the same value, I would have 2 times 5, which is 10. dc dt is negative 0.1. 2 times 5 times 5 is 50. Sine of, now if we have an equilateral triangle, that angle would be 60 degrees, which is equivalent to pi over 3 dc dt. So I get negative 1 is equal to 50 times sine of pi over 3. Sine of pi over 3 is equal to square root of 3 over 2. So 50 times that is 25 root 3. So dc dt is equal to negative 1 over 25 root 3, which is equivalent to negative 0.0231 to 3 sig figs radians per second. Okay, there you have it, guys. That's related rate, dealing with changing angles and sides, a couple different scenarios there. Please let me know if you got any questions. Otherwise, we'll see you in the next video.